Welcome to our webinar Selectivity Line Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I am happy to guide you through this session of the webinar. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I am part of Siemens Power Academy in Nuremberg as a certified trainer for protection. And today I'm introducing you to Selectivity in Line Protection lectures. What does the application look like in transformer differential protection? And what does the application look like in busbar differential protection? And since we receive one question rather often, yes, we will record the webinar and make the recording available and the slides to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your questions during the dedicated Q&A session after the series on 21st of June. In addition to me reading aloud your questions, you could also chat with your experts in the background. Please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now let me introduce our expert, Professor Dr. Siegfried Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH Aachen University. He joined Siemens in 1986. For many years he was head of the product lifecycle management for protection, where he was deeply involved in the design of the C-Protect 4 and the C-Protect 5 relay families. Within a master course of power engineering at Brandenburg University of Technology, Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens, but continued his university lectures. Siegfried, and now we are curious to learn more about selectivity in protection. The stage is yours.
Let's have a look into transformer differential protection. That means applying our differential principle to transformers. Remember the principle, we draw a circle around our device, measure all currents flowing into the device and calculate from that the differential current by summing up the currents. If we apply that to a transformer, we have to consider a few things. Of course, the transformer has a winding ratio. That means the current flowing into the transformer on one side, into a healthy transformer on one side, is not equal to the current flowing out of the transformer on the other side, because the transformer has a winding ratio. That can be taken into account by telling the protection relay what the winding ratio is. Then the transformer may have tapping. That means the winding ratio may change depending on what the tapping is. That is a little bit a disturbing thing. The big thing is this one, the phase shift. If you look at that transformer here, that is a star delta transformer, the current on the right side and the current on the left side have a phase shift. That means they don't have the same phase, and that comes from the connection of the windings here, from the star delta connection, and it depends on how the transformer is built. You may know we have different types of transformer and they have different phase shift. And that means before we can compare or can apply the differential protection to our currents, we have somehow to compensate this phase shift. Otherwise, we get a differential current already coming from the phase shift. And then we have two more issues there, which I will touch later on in the presentation. We have to do special treatment of zero sequence currents, and we have to look at the so-called inrush. But let's look a little bit more into this phase shift issue, and I would just like to give you an example which illustrates how this connection of windings influences the current flow. And for this, I would like to take this picture. You see here a delta star transformer. That means on the left side we have a delta connected winding, and on the right side we have a star connected winding. And we assume here that we have a phase-to-phase fault on the secondary side, as indicated here. And this phase-to-phase fault, we assume we have no load current flowing. This phase-to-phase fault gives us a current flow where two windings of the secondary side are affected. That means our two current transformers on the secondary side measure just simply the short circuit current. What is now seen on the primary side? And to evaluate that, the way of thinking is as follows. Look at the secondary winding 1. We have a short circuit current flowing there. And if we have a short circuit current flowing in winding 1 of the right side, we must have a transformed current in winding 1 on the left side. That means we will also have short circuit current flowing in winding 1 on the left side as indicated here. Same applies to winding 2 on the right side. We must also have a current flow as indicated here on winding 2 on the left side. Winding 3 of the right side has no current flow. That means we also have no current flow on the left side. And if you look at that, if you draw these arrows and look how the current flow is on the left side, you suddenly see on the right side we have a two-phase fault, and on the left side we have current flow, short circuit current flow in all three phases. And that is just the physics of the transformer. And you can imagine if you apply the differential protection concept to that, you will always see, for instance in this case, a differential current just coming from this strange behavior of the windings. The reason for that is that the current transformer do not show the current in the windings. If you look at for the delta side, if you look at the left side, the current transformers are installed at the terminal of the transformer, but they do not measure the current in the windings. And that has to be compensated by the algorithms. And to do that, some matrix operations with the measured values are required. And I don't want to show you here big matrices. I just want to show how the thing basically works. We measure the currents on both sides of the transformer. We give that to our protection relay. Then we do an adaptation of transformer ratio, current transformer ratio, and so on. So to standardize all measured values on a common level so that they can be compared. Then we may need a certain zero sequence current treatment. I will discuss that later. And then we have to do the compensation of the vector group to eliminate this disturbing thing we just discussed on the last slide. And then we end up with transformed current values, and there we can then apply the normal differential algorithm as we discussed it before, with differential current and restraint current and so on. That means we do a number of transformations. we end up with transformed currents, and there we can apply the normal differential principle. As shown here, calculate the differential current. If we have a fault in the protected line, we will again be on our 45-degree line in the diagram. That means here in transformer differential protection, we use the traditional concept using differential current and restraint current. If we have normal operation, the operating point is somewhere down there near the origin. Theoretically, it is on the horizontal axis. Practically, you have always some errors from current transformers, tap changes, in this case also magnetizing current, which causes some errors. And then we again have to discuss the external fault outside the transformer, where we have a high current flow through the transformer that increases the restraint current. We also have increased measurement errors in the current transformers that brings us up a bit, and we must tune this tripping area in a way that we don't come into the tripping area from these measurement errors of the current transformers. This plot shows just the principal thing, differential and restraint current diagram. In reality, the diagram in our protection relays look like this. That means we have a stepped characteristic. Remember what I told in line protection. There also we represent the current transformers with two different values. You have the same thing here. This characteristic has to be adjusted again based on the estimation of errors we have if we have no fault in the transformer. In the traditional concept, you do it a little bit in an indirect way, but the way of thinking is the same. You have error coming from the magnetizing current. It's similar to differential current resulting from line capacities for line protection. Then we have some errors coming from the tap changer, which means that the winding ratio deviates from the standard ratio. And then we have current transformer errors, and they increase more than linear with the current. And from that we can make an estimation of the total error, and then we calculate a stepped characteristic so that we have a certain security margin there. So that is how the thing works. Now we have to look at two issues which additionally have to be taken into account. One thing is the problem with zero sequence current in YND transformers. That means in transformers where we have one side with a star connection, where the star point is grounded, and the other side a delta connection. In these transformers, you may have a zero sequence system on one side. That means the sum of all currents flowing into the transformer on one side may deviate from zero because part of the current flows to the star point. On the delta side, you have no star point connection. That means there is no current flow to ground. And that means the sum of the currents on the delta side is always zero. That means you have no zero sequence current on the delta side. And that causes trouble if you apply the normal principle, and that has to be compensated, as we also have to compensate the vector group issue. And there are two possibilities to compensate that. One possibility is to eliminate this zero sequence system. That means we measure the currents on the star side, eliminate the zero sequence system, and then continue the whole thing with eliminated zero sequence system. then we have currents from both sides without a zero sequence system, and they can be managed as discussed before. That is possible. That reduces a bit the sensitivity for internal faults, but you have to do that if you are not able to measure the current in the grounded star point. If you are able to measure the current, that means you have an additional current transformer which measures the star point current, then it is possible to correct that without affecting the sensitivity. That means then we apply a correction operation in our algorithm which takes the measured star point current out of the current so that both currents from both sides can be compared. Then, as I said, the sensitivity is not affected. The disadvantage is you need a current transformer in the star point. That means either you need an additional current transformer or you have a little bit a reduced sensitivity, depending for every application that has to be decided. That was the issue with the zero sequence currents. And another issue in current transformer protection is the inrush. What is an inrush? Imagine you have a transformer which is not energized, maybe secondary side is open, and now you close the breaker on the primary side and you energize the transformer. And what then happens is plotted here in this diagram. You suddenly see, although nothing is connected on the secondary side, you see pretty high currents flowing there. And the range here of these diagrams is around 1000 amps. There's current flowing into the transformer. You see it decreases a bit. It's different in the phases because the amount of current you see there depends on the angle where the circuit breaker is closed. And if it is simultaneously closed on all three phases, that means in all three phases you have a little bit different behavior. And then it takes a few seconds, and after that the current disappears. So what does that mean for differential protection? That's a typical situation. You have current from one side, the other side has current zero, and that means you calculate a differential current, and with this differential current you may be in the tripping zone, and you may trip. But that is not a short circuit, it's not a fault, it's a normal behavior of a transformer. So the inrush is a normal effect, no tripping allowed. But if we just apply the differential algorithm, it would trip. So what can we do? Not a good idea would be say, okay, if the differential protection trip, we switch off the protection relay, energize the transformer, wait until this is gone, and then reactivate the protection relay. Then we would get the transformer in operation. But why do we have the protection relay? We could have a fault in a short circuit in the transformer. Somewhere in the bushing, an earth fault or whatever. And then energizing it without protection running is not a good idea. We might burn down the transformer. The whole thing might explode. So never do that. That means we must think about something else. And a typical thing which is traditionally done to detect this inrush and to distinguish differential current coming from inrush from differential current resulting from a short circuit, a typical approach is the use of the second harmonic. If you look at these current plots, you see that are not really sine waves. There is a high content of second harmonic in these currents, and that is a good criterion. That means we do a permanent Fourier analysis, and if we suddenly see differential current with a high content of second harmonic, then we say, okay, it looks like an inrush. We block the protection or part of the protection, the sensitive part of protection, for a while until it disappears. So the use of second harmonic is this has been used for decades already. What we realized in recent times is that due to optimization of the transformer design and also resulting from new magnetic materials in the transformer, this second harmonic criterion turned out to be a bit difficult to set. Because you must figure out what should be the level above which you say that is an inrush, and it became more and more critical to figure out the right value. And for that reason, we are now using an additional approach to detect that thing, the so-called current wave shape analysis. That means we look at the pattern of the current curve, and there are special features you have in this pattern which are characteristic for an inrush, and this pattern analysis is then used to block the protection in case of an inrush. Important thing is blocking of protection is always a critical thing. That means this is not just a tiny little bifunction. Blocking is always critical because you must always make up your mind, is there a certain risk that you make a wrong blocking of a protection? That means if you have in reality a short circuit and then your algorithm suddenly says, oh, it looks like an inrush, and you block the protection, you have a missing operation of your protection. That means these algorithms for inrush detections are very sensitive things. They must be treated and tested very carefully so that you don't do a wrong blocking. Normally the blocking affects only the sensitive part of the algorithms. That means there is no risk that high current faults are also blocks, but nevertheless that is a sensitive thing. Of course, differential protection also for transformer has a certain sensitivity limit. Now you saw we have differential currents coming from tapping, from magnetizing current, from current transformers. It has a certain sensitivity limit, and there is, for instance, one type of fault where this sensitivity limit may disturb us. That is a winding fault. Imagine we have a fault on the secondary winding. If the ground fault is from the terminals to ground, you have a high short circuit current because you have the full voltage of the secondary side driving this current. But the fault point can be anywhere in the winding. It can be from the middle of the winding to ground or lower down. And the critical thing is to have a fault between only a few windings and ground. And if you calculate that, if you apply the normal differential algorithm on such a case where you have a short circuit between only a few windings and ground, you would find yourself somewhere near the origin in this diagram, but still in the green area. That means a normal differential protection would not trip on this fault. And for that reason, you find in many transformer protection applications special protection scheme which has been tuned into this direction, and that is the so-called restricted earth fault protection. And the idea is there You design this restricted earth fault protection for one side of the transformer only. You measure the star point current and you measure the phase currents, and then you set up an algorithm based on these measurements. And that is able to detect ground faults in the winding a bit more sensitive than the normal differential protection will do that. It covers one winding only the winding with the star point, but it can be more sensitive. You need, again, here a current transformer to do that, and of course you need also the algorithm, which is normally available in our protection relay. That was a short look to transformer differential protection, and the last chapter which will follow later on is the busbar differential protection. The fourth chapter in the differential protection session is a look into busbar differential protection. Simplest approach is this: you have a single busbar with a number of feeders, and then the application of the differential protection is pretty easy. We typically use the traditional scheme. That means we calculate the differential current and the restraint current. In busbar protection, we use this, we apply the differential concept with instantaneous values. That means we use just individual samples, and with the samples we calculate the differential current and the restraint current, and then we go into the tripping characteristic. And it looks very easy if you look at such a busbar. Of course, we have to do that phase by phase. We have no problem with transmitting measured values over 50 kilometer. We have no problems with vector groups and all these things we discussed before. So for busbar protection, it looks pretty simple, but there are a few things also to consider here which make life a bit more interesting. One thing is, we will see we will have some special challenges in the algorithm. And the point with busbar protection is, if you have a wrong operation in line protection, it's not good. Your boss maybe will ask you a few questions. You lose one line, but normally it's not such a critical thing. If something goes wrong in a busbar protection, if you have a wrong trip in a busbar protection, you lose many lines. You lose all lines connected to that busbar. That means anything going wrong in busbar protection typically has much higher impact on our power systems. So busbar protection must be handled pretty carefully, and we will see we have some challenges in the algorithm. The topology of the plant is typically not that easy, as you see that in this picture here. Plants can be double busbar, triple busbar, and there are a few other things you have to take into account. And the last thing is also, if you have an outdoor substation, it can be a big substation where the distances are long, so you have to make up your mind where are you going to arrange the components. So let's first of all look into the challenges of the algorithm. I will start with a few examples. That is the characteristic we use. You see it's a little bit different from this symbolic thing I normally use. That is the characteristic we use, and in this case our characteristic is very simple. We just have a slope of our tripping area, and near the origin a certain cutoff thing. You also see the 45-degree line. If we have a fault on the busbar, we are on the line. So let's discuss the different cases. First of all, the internal fault. We calculate the differential current, we calculate the restraint current. in this case both are equal, and we are on this 45-degree line, internal fault, clear in the tripping area, we will trip. That's easy, that's normally work. Again, in busbar protection, normally the problem is always avoid wrong tripping, not to trip in case of a fault. That is typically the easier part of the story. So let's look at an external fault. We have here the busbar. We have a fault in one feeder, and that means we have fault current, in this case, coming via the two feeders to the busbar and then flowing into our external fault. That means the current transformer in the rightmost feeder sees outgoing current equal to the sum of the two other currents. That means if we calculate the differential current, I1 plus I2 plus I3, I3 is minus I1 plus I2, so the result is 0. That means the differential current is 0. The restrained current is I1 plus I2 plus I3. That means our operating point is somewhere there on the horizontal axis. Easy, no trip. We are clear outside the tripping area. And now let's assume what can be the critical situation for that. The critical situation is you have a big busbar with a high short circuit power, and on this busbar you have one auxiliary feeder which does just some local supply. That means you have a pretty small current transformer. And if you now have on this feeder an external fault, that means the whole short circuit power of the busbar goes through our poor little current transformer for the auxiliary feeder, and it drives it within a very short time into saturation, and the output signal of this current transformer will look like this. You see here in black the current it should show, but after a few milliseconds it says, oh, too much current, output is 0. To make it simple, we can say after some time the output of this current transformer is 0. What does that mean for our protection relay? Without saturation we had differential current is I1 plus I2 plus I3. The sum was 0 because I3 was minus I1 plus I2. If we now have saturation, we assume the current transformer at feeder 3 doesn't give any output signal because it's in saturation. Then the differential current, we calculate from that, because now I3 is missing, is only I1 plus I2. Also the restrained current is I1 plus I2. And that means our operating point now moves from here up into the tripping area based on this saturation effect. And that, of course, is the thing which has to be avoided. Now, we have a short circuit on an outgoing feeder, and we would expect that the outgoing feeder protection trips and not our busbar, because then we would lose the whole busbar. That means we must do something in this situation to avoid a wrong tripping. And that is a challenge for the algorithm. And what you can, or what we normally do in this situation, is we look at the very first milliseconds. That means we assume that in the first few milliseconds there is no saturation of the current transformer. That means we look at this point here, and from there we make a decision. And if in the first milliseconds it looks like an external fault, differential current is 0, and then suddenly our operating point moves into the tripping characteristic, it's very likely that it is a saturation effect. And that means we should somehow block the algorithm. That means we first see an external fault and suddenly this thing moves into the characteristic, then we block it. But also there we must always be careful with blocking, because we can also have the situation that we have an external fault, maybe there is an exploding current transformer or whatever, and the parts fly onto the bus bar, and 10 milliseconds later this external fault evolves to an internal fault. And if we then block the busbar protection, we would not catch the internal fault. That means this blocking is always a little bit a critical thing. What we typically do is we make this decision before the first saturation comes. That means we have some requirements to the current transformer that we must have a saturation-free time of a few milliseconds. You find this requirement in the manual. And then we do blocking of a fast algorithm, and we activate then algorithms with longer data windows which are not that sensitive on saturation. You can do some 2 out of 2 measurement or whatever, which avoid wrong tripping on one side, but on the other side, they allow, if the fault really evolves from an external fault into an internal fault, which allow, in this case, a tripping of this internal fault. Maybe a little bit delayed, but it should still be tripped. You see, there is some challenge in the algorithms there, especially because normally the requirement for busbar protection is it should be very fast. We are talking here really about milliseconds. We have for the reaction time, of course, you have to add to that before you have the tripping time, the breakers have to open and so on. But busbar protection is the type of protection with really the highest requirements concerning tripping time. That were the challenges concerning the algorithm. Another challenge is concerning the topology of the plant. And this can be very different. It can also be very complicated. What I show here is just one step further. Instead of having one busbar only, this is a double busbar substation. And in this substation, you see every feeder has a circuit breaker and has 2 isolators, and with these isolators you can connect the feeder either to the green busbar or to the purple busbar. And of course, in such a substation you would like to have a busbar protection separately for the 2 busbars. That means if you detect a short circuit on busbar A, you would like to trip only the feeders which are connected to busbar A. And the same applies to busbar B. Not if you see a fault on one of the busbars, you trip all breakers around there. That's not a good idea. So we must be selective. Only the affected busbar or only the feeders which are connected to the affected busbar must be tripped. And that makes the whole thing a bit more complicated, and I have indicated this in this diagram. In the current transformers indicated with these circles on the lower part, I have indicated by color to which busbar the feeder is connected. So you see the 2 leftmost feeders are connected to busbar B, to the green one. Then the third one is connected to the purple busbar, and so on. And then virtually we must connect all green current transformers to one algorithm where we calculate the differential current and the restraint current, and all feeders connected to the purple busbar. All these currents are combined into another algorithm. You see here, for instance, this feeder, one isolator is closed, the other one is open. That means we must take into account the position of all isolators to find out, is this measured current now part of the green equation or part of the purple equation? This one would be, this current measured in this feeder would have to go into the calculation for the green busbar, and the other one on this side would go into the calculation for the purple busbar. So it's not really rocket science, but such a busbar can be even more complicated, can even have more feeders. That means you end up in a lot of wiring and contacts and so on, and there is always a risk that something in this topology information is wrong. And now it's important that we avoid that wrong topology information does not lead to wrong trips. That means we must implement in busbar protection a few good ideas to avoid wrong tripping just because of wrong topology information. Wrong topology information means the algorithm thinks the feeder is connected to the green busbar, but in reality it's connected, for instance, to the purple busbar. And the reason for that can be broken wires. No, if it is a big substation, there's a lot of wiring down into the field where you need the position of all the isolators. We can also have failing contacts. These isolators are outside. They may become old, and contacts can sometimes fail. So this has to be detected before we make a wrong trip. And we also have sometimes switching actions. For instance, maybe we want to change one feeder from the green busbar to the purple busbar. And that means we start operating circuit breakers and isolators to do these transitions. And that means we have intermediate states. That means states where it's not really clear, is the isolator already connected to that one or is it still with this one? And also these intermediate states have to be taken into account, and the whole protection system must be safe against wrong trips just based on this wrong topology information in these intermediate states. And you can imagine there's a lot of experience which has to go into such a protection technology. One thing which helps us there is the use of a so-called check zone. What is that? I show here again these two busbars, the purple busbar and the green busbar. We set up our equations, differential current and restraint current, separately for the green and for the purple busbar, taking into account the topology information. And the idea is now to define a yellow zone which goes around the whole thing and which calculates the differential current and the restraint current across all feeders without taking into account topology information. And then the tripping condition is we will only trip if, for instance, the purple zone says, I see a fault, I am in the tripping area, and also the check zone says, yes, I also see that fault. I don't know where it is, maybe on the green or on the purple one, but I also see a fault. Then we are pretty sure that there is a short circuit. If only the purple zone says, I see a fault, and the yellow zone says, I see no fault, then there is a certain risk that the fault indication results from a wrong topology. So the check zone, which is a standard feature, helps us to avoid wrong tripping because of wrong topology information. So that was the second challenge we have. And the third one is an easier one. That is the question, where are the components? And I show here in these two pictures the possibilities we have. On the left hand, we see a centralized busbar protection. That means we have one device, one protection relay there, and all current transformers, all contacts from isolators and so on. In this case, it's even a triple busbar thing. Everything is wired to our single device. This can make sense, or this makes sense for maybe smaller substations, especially for indoor, where the distances are not that high. That's called the centralized protection, because everything is wired to one central point. On the right side, you have the so-called distributed busbar protection. What is the difference there? The equation for differential and restraint current, they always have to be done on a central point. That means we must always have one device where everything comes together. But for the distributed busbar protection, the data acquisition is distributed, decentralized. And what helps us there, that in the feeders, for the feeders, we need feeder protection anyhow. There can be distance protection or overcurrent protection or whatever. That means we already have protection relays there who do the data acquisition. Or we install a separate device just for data acquisition for busbar protection, like we had it, for instance, in the previous generation. And then we have a communication system which delivers everything, all sampled values, to the central point where we run the protection algorithm. In the previous generation, we had there a star connected thing. That means we had point-to-point connection from the central unit to all feeder units. With CProtect 5, we have now this ring-type communication available because we make there use of modern process bus technology. You need a redundant high-speed optical fiber, but it's powerful enough to calculate, to bring all the sampled values to a central point, even for a bigger substation. And you see, this reduces the amount of copper wiring if the feeder units are located closer to the switchgear. That means it depends a little bit on the layout of the plant, whether you take the centralized or the distributed concept. That was a look into busbar protection. And with that, we come to the end of the differential protection session. Thank you for listening.
Thank you, Siegfried. It has been an interesting session. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on 21st of June. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through the session on selectivity in line protection. In this session, we learned how the application looks like in transformer differential protection and how the application looks like in busbar differential protection. I'm looking forward to meeting you soon in the Q&A session of our series on June 21, where we will answer your questions from the webinar Basics and Selectivity in Protection. Stay safe and sound, take care, and goodbye.